Hi and welcome to another edition of Ask the Expert. Today we're joined by Pete Wood from DesignSpark and Ben Lampe from Maxim. We're here today to talk about DC to DC power design using Maxim's free EE-Sim tool and Oasis design tools. Hi guys, welcome to DesignSpark.
I'm Pete Wood. I'm part of the DesignSpark team, been with the team for almost 10 years and been in the design engineering community for over 20.
Hey guys, yeah, thanks for having me. So I'm an applications engineer at Maxim Integrated. I've been there for a little over 2 years now, and I'm working on the simulation models for the EE-Sim power supply tool. I got my bachelor's in electrical engineering from Santa Clara University, where I'm also doing a master's degree, and I also teach some undergraduate power and analog electronics labs there.
So we've got a couple of questions to put to you today, to Ben, and hopefully, during the conversation we can get quite a lot of information out to our users. With all design tools and simulation tools, they are essentially about making the engineer's life a lot easier and saving a lot of valuable design time. So with your design tools, what would be the steps that an engineer should take to make sure that they get a working design at the end of their efforts?
So a power supply is like any kind of electronics. You're gonna have to start with a design. You have to pick your components, put together a schematic, and ideally from there you want to start getting some simulations together just to prove that it works how you expect it'll work. From there, it's kind of moving on to layout. You got to take your measurements, make sure that the physical board matches up with the expectations that your simulation sets. And part of that, is comparing back to the simulation, which is a stage that I like to call correlation, making sure that there are no surprises within your measurements by holding onto the simulations and going back and comparing.
Okay. So what would be kind of the first basic step for somebody to take?
Yeah, so as far as first steps, you need to come up with your design first. So a lot of times it's using design equations in the data sheet, but we've got a pretty neat tool that I've been working on, EE-Sim, that tries to simplify those first few steps as much as possible. So the idea there is if you have an idea for your power design, you pick a chip, you enter in all of your design parameters. What's your input voltage range? What's your output voltage, output current? You can go in and do some more detailed specs. What's your output ripple? If you have a load step, what kind of overshoot, undershoot do you want?
Yeah.
You can optimize for size, efficiency, cost. And then the tool comes out and designs a power supply for you. It gives you a schematic, lets you run all the simulations, and it gives you a full bill of materials. So all those first few steps taken care of just within 5 to 10 minutes.
And what would be some of the kind of key simulations that users should be running within the tool?
So the two simulations that I tend to think are the most critical are a load step and an AC analysis. The load step tells you when you get hit with the load transient, what's going to happen, how long does it take to settle, how much is your output going to deviate. So you want to set that up for a worst case and make sure your power supply is going to handle that worst case. And the other thing was the AC analysis, and that tells you all about the stability. Your stability, it tells you about your bandwidth. You can read a lot off of the Bode plot if you know what you're looking for, and it's really helpful for going back and figuring out which components are having what effect on the overall performance of the supply.
Yeah.
Beyond those, we do have some other simulations you can run that are also great for figuring out in certain circumstances how your power supply is going to run. You can run a steady state in EESim. You can do line transients. You can look at the startup behavior, see how the soft start's working.
Yeah.
And we also let you run some efficiency tests. So look at how the efficiency of the converter will change with load current.
This sounds like it could be a great tool for, less experienced engineers in kind of power design. and also I guess seasoned engineers as well, to sort of give them a bit of a shortcut, a bit of a faster way to sort of find the right device, and a lot less aggravation than trying to do it without something that's sophisticated. But I guess, what sort of tips have you got to help, I guess, engineers get the most out of that kind of, accurate simulation? Are there any kind of things, sort of rules they should follow, or, is it pretty intuitive when you step through this design that sort of guides you all the way, so that at the end result, you are hopefully guaranteed something that performs as well in real life that it does on the actual simulation?
Yeah, so whenever you're simulating, the tricky part is understanding and accounting for any of the non-idealities that are going to show up on your board. And so you have to take note of what is and is not modeled within the power supply first, so you're not going to be operating in any sort of modes that aren't modeled within the power supply. So that's the first thing to kind of look out for. We leave notes on there of which features we model and which features we don't model, just so that you can keep track of that. The other thing you always need to make sure when you're doing simulations is that you're using realistic models for the components. So for the inductor, make sure you're modeling a DCR. All of your capacitors are going to have some equivalent series resistance.
Yeah.
And especially if you're using ceramic capacitors, you have to account for the DC voltage derating, because the capacitance rolls off pretty significantly with DC voltage. Yeah, and these are all things that are handled within the tool. The tool, basically, when it's picking components, will check DCR, make sure you're not going to hit any saturation or RMS current limits in the inductor. It will derate all the capacitors for you, and it will make sure that everything is kosher on those aspects. There's EESim is the online design tool, so you can use that to create your design and run some basic simulations. And we also have a free offline tool that you can download called Oasis, which offers that similar functionality where you're able to go in and change stuff and probe whatever you want to.
So can you show us then just an example then of what the tool looks like?
Yeah, so when you pop open EESim, here's the landing page. We have a selector tool that you can use based on your inputs and outputs. It will help you select a chip, but if you already know what kind of a chip you want, you can head down here. And so let's just start a sample design. Let's do Max 17242. There we go. So once you get that opened up, it comes to this design requirements page, and this is where you can put in all of the requirements that you want to meet. So for input, you have your minimum, maximum, and nominal, and you can add an input voltage ripple if you want. That'll help size those input capacitors. Output, so we've got an externally resistor adjustable, or there are some fixed voltage versions for this part. I'm just going to keep all this stuff by default, but you've got all sorts of parameters on the output requirements where you can look at the output ripple, what your load step is going to look like, how quick it's going to hit, and what kind of overshoot, undershoot you want there. And again, you've got your design trade-offs, which is how do you want the part to select components for you. And then you've got some extra stuff down here. If you want to choose the mode of operation, switching frequency. But once you're satisfied with everything, you can just go ahead and hit Create Design. It'll take just a minute to pick all your components, populate a schematic. And there we have it. There's your power supply.
Yeah, wow.
Great.
Yep. And if you want to go in and tune things, you can go look at the specific components, change them out if you want, and then when you're ready, you can go ahead and run your simulations. So here are all those different simulations I was talking about. So we can run like a load step, an AC loop, run some efficiency calculations. And you have control panel over here to adjust any of the parameters that you're looking to adjust, and tune your simulations however you want to.
Yeah.
But yeah, it's Pretty
So you
simple
really,
to go.
yeah, you really can go in there and fine tune. Yeah.
Yep.
And for an online tool, that is pretty impressive, right? I mean, that's quite a powerful online tool. And the Oasis tool, which is the downloadable version, you can just do some more sophisticated things, I guess, right, than you can in this online tool.
Yeah, so with this online tool, we give you the schematic. You can go in and change some components. You can redesign. This is mainly intended to be kind of the design aspect, where it will spit out your simulation and your schematic. So here's an example from that. You can take a look. And there we have, there's our output load step. Yeah, whereas for the Oasis is mainly meant as your standard simulator experience.
Yeah.
So I don't have a toolbox over here where I can go and add more components.
Okay.
But what I can do is you can go ahead and actually download the schematic you generate here and then open it up in Oasis. And that gives you the more traditional simulator experience where it's not the design tool. That's mainly for poking, adding, and testing some things beyond the limits of what we allow you to do within.
So once a designer's satisfied with the simulation, Ben, how can they make sure that the physical board will give them the same performance?
Okay, so once you have your simulations ready to go, it's mainly a matter of following the proper layout guidelines. But then once you do have a board, you do want to make sure that it matches up with the simulations to make sure that the expectations set by the simulations are met by the board. And that really comes down to taking some measurements on the board and being able to correlate that back to the simulation.
Yeah.
You don't want to ditch the simulations once you have the hardware. They're still valuable first as a reference, and secondly, to be able to go back and model any unanticipated results that you might get from the hardware.
Right.
So if you get something in the hardware that doesn't look like the simulation, if you're able to figure out why, you can go back to the simulation again and remodel it and make sure it's not going to be something that breaks your design.
Yeah.
Okay. Okay.
Yeah.
So what would be the kinds of measurements that the engineer should make on the power supply itself then?
So aside from the generic smoke test, plug it in, make sure it works, probe your steady state waveforms, it's pretty much the same thing as from the simulation. You want to do a load step, which will show you any overshoot, undershoot, settling time issues. But in order to really debug, I think it's really beneficial to go ahead and take an AC analysis on the hardware as well.
Yeah.
AC is one of those analyses that tends to be dropped once you run it in the simulator and get a phase margin out of it. But it's really helpful in terms of identifying any discrepancies between the hardware and the simulation. Because it goes in, it models every pole, every zero. You can see on the plot, and so if something's off, it will show you exactly which one, as opposed to looking at your load step and trying to figure out what exactly is causing a little bit more overshoot than you expected.
Right. Okay. Yeah. So in terms of design then, what would be some of the common measurement areas to watch out for? So things like parasitic layout, for example, is that taken into consideration with the design tool?
So the design tool takes into account some of that. When we run our design, when the tool runs the design equations, and when it calculates efficiency, it does account for some ideal trace resistance, for example. But at the end of the day, the design is going to rely upon being able to put together a layout that works for the design.
Yeah.
So you need to make sure you're following all those main layout guidelines, to keeping a big, low impedance ground plane, paying attention to any switching current loops and making sure those are made as small as possible, keeping your capacitors close. All those things still apply. And then when you go to measure that stuff, there are some things that you do need to watch out for. So in terms of those parasitics, it's not just in the layout, it can also be within the measurement. So
Okay.
when you go and take a load step analysis, you want to make sure that, for instance, the load doesn't have any really long leads to
Yeah.
the board, because those are going to add inductance. They're going to
Absolutely.
slow the ramp time, and your converter is actually going to start responding to the load step before the load step's finished, and so you don't get a really nice clean look at what that response is. Other things, just like making sure that you're measuring output voltage directly across the output capacitor, and trying to minimize the loop caused by your probe.
Yeah.
So instead of using the tail ground clip with the alligator clip, that leaves a lot of area, which can add some inductance, and it will actually accentuate high frequency ringing noise.
Yeah.
So making sure that you use a ground spring or something along those lines that can connect directly across the output capacitor when you're taking that measurement.
Yeah, these are little things that people sometimes tend to overlook, aren't they?
Yeah, definitely. Yep, and they will show up. They'll make things look worse than they actually are. And so that's definitely one of the first things when people are struggling to get their board to line up with simulations. One of the first things I always ask is, well, how are you taking the measurement? Can you give me a picture of the test setup? Just to make sure that what you're getting out of the test equipment is what's actually there. AC analysis, I don't see people doing too often because it does require some specialized equipment, but if you do have access to a vector network analyzer, it's one of the best, easiest, fastest ways to analyze your power supply performance and get some really granular detail about what exactly is going on the board.
One of the things that I used to notice when I was involved in test and measurement, not power design, but in test and measurement, it wasn't actually the circuits which were the problem. It could have been the equipment itself. It's not calibrated, or it's poor quality, and even sometimes things like you were mentioning test leads earlier. You've got to make sure that you have good quality equipment when certainly doing analysis on circuits.
Yep. Little things like making sure that the bandwidth of your scope and probe matches up with the signals you're trying to measure. If you are doing any kind of differential measurement across two different probes, you got to make sure that they're matched probes.
Absolutely.
Or else they're going to introduce their own errors. There are lots of different potential stumbling blocks. And so it's just making sure that you understand the physics and the electronics of that are applied to the test setup by the measurement equipment.
So I guess there's two key things. Let's pick. What are the two key things you should look at if your measurements aren't stacking well? What are the two most common things that affect that? I mean, you've mentioned about the test equipment setup and stuff, but are there any others that kind of spring to mind that are fundamentals that you often find that always crop up when somebody's got a problem? It's always this or that as the number thing.
Yeah, so discrepancies typically come back to either a measurement issue or some sort of parasitic that wasn't initially modeled. So going back and say you didn't know how much the output capacitor was going to derate. And that's something that you can actually see pretty clearly in like an AC analysis. If the pull caused by that filter capacitor is happening earlier in your simulation and much later, odds are that capacitor is a lot smaller in your circuit, and maybe you didn't account for all of the DC rating that it was going to go under. Or it could just be a slower piece of silicon. There are all sorts of different things that can happen that aren't necessarily accounted for within the simulation.
There was one other thing I wanted to mention. It was about from your test equipment, if you can use the waveform, export that from your test equipment as ASCII data, you can put that into the simulation tool. Is that right?
Yeah, definitely. That's, I think, the easiest way when you're trying to do correlation. A lot of times people will have one for their measurement where they're looking at the screenshot of the scope, and another where they're looking at the simulation. But you can actually take most measurement tools now have some sort of digital storage, which allows you to save the waveforms and export them. And if you know the kind of the format for the waveforms that your simulator uses, you can copy paste those waveforms directly into the simulator window.
That's the Oasis one, I take it, the offline one rather than the online version. Is that right? Okay.
Yeah, and I've got an example of that if you want to.
Sure.
That'd be great.
This is an example of one of the converters I was looking at. So here I actually I split up the AC analysis into 3 different blocks. So down here is what you'd think of as your typical loop analysis, and then I basically split it up into 2 blocks, which is the power modulator block and the compensator, which is the air amplifier. And I have that here if you want to check it out. So this is the circuit that I was using to generate that stuff. So essentially this right here is what you'd think of doing when you're doing your normal AC analysis. You have an AC probe that's injecting a signal into your feedback loop, and then you have a measurement that's taking that injected signal as your input and the output voltage as your output. That is good. It gives you your full loop response, but when you're trying to go in and debug and figure out exactly what's causing what, it helps to have a little bit more granularity. And so you can add a couple extra probes here. So I've added 1 probe here that takes the injected signal as the input, and this compensation pin, which is the output of the error amplifier. And so this is just looking at the error amplifier and those compensation components. And then this one likewise takes the error voltage as the input and then looks at the output voltage. So this part is just looking at that modulator. So what it ends up seeing, what I've got here is the black curves were the simulations. The colored curves were signals that I actually imported. And so we've got down here is the full loop response, and it looks pretty close, but you can see at this black curve up is a pretty big gap from where it's supposed to be down here. And when you split that up, you can see, okay, this is the power block right here. Everything looks pretty clean in the power block. It's those simulations are right on top of each other, and it's when you go up to the compensator where things started to deviate a little bit. And so this ended up being just a issue with the error amplifier gain in the simulation versus the silicon. Those things do have some tolerance to them, and so basically I was able to go in to the transconductance gain of that error amplifier, play around with that in the output resistance, and ended up with something that looked much cleaner. So here's the modulator now lining up. And then from there, you can go rerun the simulations now that you know what the actual board is giving you. And make sure that nothing's going to deviate beyond expectations. And so that was one of the other things that I added here, was looking at the range of possible load step responses, just using a little sweep. And so swept output capacitance over tolerance, inductance over tolerance, and then this gain discrepancy that I found over an expected tolerance, and just looking at the different responses you can get and making sure that none of them are going to fall outside of what is what's allowable for your design.
So what we'll do, we'll put some links down below as well, so our users can go onto your site and download the software. I really do appreciate the time that you spent today, Ben, showing us just how powerful both your tools are. And again, just like to emphasize, empower design free of charge simulation tools to get you up and running, and the support networks that are there. Check out Maxim website for any additional information. And I'd just like to thank you again for joining, and I think we'll talk again quite soon, Ben.
Yeah, thanks for having me.
You're welcome. Cheers. Good to see you, Ben. Thank you.
All right.